Hi everybody, my name is Simon and I want to talk about graphics programming, especially the tools and frameworks that are available for creating interactive 3D applications. Today, if you want to create an application that involves interactive 3D graphics, you basically have two choices. Either you use your favorite game engine or you use a low-level graphics API like DirectX, Vulkan or Metal. Whichever is best highly depends on your specific use case. Game engines are great because they have a ton of built-in functionality that lets you get started really quickly. However, they are also extremely complex beasts, and understanding how everything connects under the hood can be extremely difficult. For example, I've been working at a research institute for about 6 years now, focusing on virtual reality and immersive visualization. We mostly use the Unreal Engine for all our projects, and at one time a colleague of mine needed to have an object that has the exact RGB value in the final image. This sounds very easy at first. However, all the different lighting and post-processing effects built into the Unreal Engine made it more difficult than anticipated. He needed to dig around and find out the features he actively need to disable in order to make it work. There are other examples where you need additional vertex or instance attributes for a mesh. You want to create a new render path or want to experiment with a new rendering strategy altogether. Where I have the feeling that I know how to do it using the graphics pipeline built into the GPU, but I have to actively fight the high abstraction layer by the game engine. And to be fair, it's almost always possible to implement it, but it requires in-depth knowledge of that specific engine. The other extreme is using a low-level graphics API directly. Here, you have full control about everything that's going on. However, it's also very tedious and involves a lot of repetitive work like creating and managing various GPU resources. This takes away the focus from actually implementing an awesome graphics algorithm to boring and cumbersome resource management. So, I believe that there is room for a different kind of abstraction level when it comes to interactive 3D applications. One that is very close to the graphics pipeline on modern GPUs and gives you full control. But also one that takes away all the boring stuff like resource management. So, I've spent the last year writing a custom rendering and visualization framework called Ovis. And in the remainder of this video, I want to talk about the concepts and the design decisions I made. But before talking about the framework itself, I briefly want to recap the graphics pipeline implemented on modern GPUs. Because as said before, the framework is still modeled after this level of abstraction. When we want to render something, we start with a list of vertices and their corresponding set of attributes. These are passed to the vertex shader, which outputs a position of the vertex in clip space as well as a set of values that are passed to subsequent shader stages. Then, the GPU assembles the primitive based on the vertex positions and the configuration of the pipeline, which generates either points, lines or triangles. The rasterizer then takes the primitive and generates so-called fragments for each affected pixel of the viewport. These are passed to the fragment shader, which outputs a color based on the interpolated values generated by the vertex shader. This color is then finally merged with the current content of the frame buffer by an operation called blending. This defines how the current color of the frame buffer and the color of the fragment contributes to the new pixel color. This was, of course, a very simplified explanation about what is going on inside the GPU. However, it is sufficient for now. I might do another video explaining the graphics pipeline in more detail later. The different stages of the graphics pipeline can be categorized as fixed function and programmable stages. The programmable stages, as the name suggests, allow the developer to write small programs called shaders to define their behavior. Usually, shaders are written in a different language than the actual application. All data for the shaders is passed to the GPU via buffers. The shader specifies the content of the buffers and the location it should be bound to. The application is then expected to create the appropriate buffers and bind them to the proper location. This can be error-prone because it is easy to mix up locations or to only change the buffer layout on the shader and not on the application code, or vice versa. All these problems are not complete deal breakers, but they are annoying. The Ovis framework tackles this problem by using the same programming language, Rust, for both the application code and the shader code. So, A little bit like CUDA, which lets you write code that runs on the GPU in C++, Ovis allows you to write your shaders in Rust. In addition, it automatically binds the correct buffers to the correct locations for your shaders. To better explain how this works, let's look at a concrete example. Here you can see a vertex and a fragment shader written in Rust using the Ovis framework. Shaders are just regular Rust functions prefixed by the proper attribute. These attributes will generate the corresponding shader code under the hood. The vertex shader has three inputs: a position, a color, and a transform matrix. Each input has an attribute that tells the framework where it is coming from. Here, attrib indicates that the input is a vertex attribute and res indicates other resources, but more on that later. The output of the vertex shader is a tuple with two elements. Here we see something weird. The element of the tuple are macros instead of types. This is necessary to convey additional information to the framework, as it is currently not possible in Rust to annotate the return type using attributes. The built-in macro indicates that the first element of the tuple has a special meaning. It is the screen space position of the vertex that should be used by the rasterizer. The location macro of the second tuple element indicates that this output should be passed to the fragment shader at location 0. The body of the vertex shader is very simplistic. We get the final vertex position by multiplying the input position by the transformation matrix, and we pass on the color untouched. The fragment shader is even shorter. It has a single input called color, which is annotated by the attribute location 0, which refers to the vertex shader output at location 0. The output of the fragment shader has to be a 4-component vector representing the red, green, blue, and alpha channels of the fragment color, which will be used for blending. In this example, we just set it to the input color. And that is how shaders are defined in the Ovis framework. But I'm not completely happy with the syntax yet. Especially how macros are used for the vertex shader output. An alternative would be to move the information into the vertex shader attribute like this. This has the disadvantage that information about the output type is now further away from the type itself. But I still think it makes the code more readable, so I might change this syntax in the future. Another thing I don't quite like is that vertex shader outputs are matched to fragment shader inputs using explicit locations. It is done like this in traditional shading languages, but in the future I want to do this mapping based on the name instead of a numeric location. And a small side note here. You can also call other functions from your shaders. All you need to do is add the GPU attribute to the corresponding function. The same thing is also true for custom structures. So, the same thing can be written like this, where you move the actual vertex shader computation to another function and encapsulate its input in a custom struct. Because this function can now be called on the CPU and the GPU, it makes it very easy to reuse code. Let's step back and look at the vertex shader inputs again. How does the framework know which buffers to bind based on these attributes? And how are these buffers even created? For that, we need to take a look into how the data is organized within the framework. The Ovis framework uses an adapted entity component system concept, where I myself find the term a little bit confusing, as it's not a system that involves entities and components, but rather a concept or an architecture that involves entities, components, and systems. But maybe that's just me. Anyway, it is very common in the world of game development, and it is quite simple. In an ECS architecture, the world consists of a set of objects called entities, which can be anything: the player character, enemies, walls, and so on. What an entity actually is completely defined by the components attached to it. For example, characters in a game would maybe have a position component that stores the location of the character in the world, a movement component that stores the direction the character is currently moving to, and a mesh component to convey how it is rendered. So, entities and components define the current state of the world. But for something to happen, there must also be a way to alter the state. For example, we need a way to move objects. And this is where systems come into play. Systems are basically functions that work on a subset of these components and potentially modifies them. In this example, we had the position, movement direction, and mesh component. We could now have a system that updates the position based on the movement direction and another system that takes the position and the mesh of the object to render it. The benefit of such an approach is that the systems can work independent from each other. The position update system does not care where the movement direction comes from. Is it populated by an input system that reacts to keyboard and mouse input? Or is there an AI system that controls the direction? The position update system does not care about that. It just does its job updating the position, no more, no less. The same goes for the render system. It does not care where the position is coming from, it just renders the mesh at that position. When we look at the mesh component in more detail, we see that it is actually a collection of multiple things. A mesh generally consists of an array of vertices with varying vertex attributes, an optional index buffer that defines the primitives formed by the vertices, and a set of material attributes. The Ovis framework breaks this encapsulation and uses individual components for each vertex attribute, indices, and material. In order to do so, my ECS implementation can also handle component arrays efficiently. So, when you, for example, attach the vertex position component to an entity, it not only holds a single position, but an array of positions. In this visualization, component arrays are indicated by the square brackets around their name. And because, in contrast to most ECS implementations, the components are not only accessed by the CPU, but also the GPU, the framework automatically mirrors the corresponding buffers to video memory. This way, you can easily access all components within a shader. With all this information in mind, let's get back to our program. Until now, I only showed you a part of the program. But let's have a look at the whole program that draws a triangle using the Ovis framework. I will now go through it line by line and explain what they do. The first 3 lines define the 3 components that can be attached to entities. The vertex position, which represents an array of 3-dimensional vectors. The vertex color, which represents an array of 4-dimensional vectors for the red, green, blue, and alpha channels. And finally, the transform component, which is represented by a single 4x4 matrix. The next few lines define the first system of the program. Systems are just regular Rust functions with a system attribute. The framework will then parse the types of the inputs to figure out which component this particular system accesses and calls them accordingly. This system has a single argument of the type spawn. The spawn type has a special meaning. It is a closure-like type that lets you create new entities with the specified components. In this case, calling the closure will create a new entity with a vertex position, vertex color, and transform component. In the body of the function, you can see how it is used. However, I omitted the actual values for the vertex positions and colors to make the whole program fit on screen. I don't want to get into too much detail here. I will explain the whole ECS concept of the framework in another video. All you need to know is that the system will run once at the beginning of the program and create a single entity with certain vertex positions, colors, and the identity transform. The second system, called rotate, has 2 inputs, a float and a matrix. And to give the framework the necessary information what these inputs represent, they need to have the appropriate attributes. Again, I don't want to get into too much detail here. All you need to know is that the rotate function will be called every frame for every entity that has a transform component. And it will pass a transform matrix along with the current timestamp to this function. And because the transform is passed as a mutable reference, this function can modify it as it desires. In this case, it rotates it around the z-axis based on the time. Next, there are the shaders we already know. But let's first have a look at the bottom. There, we define a third system, but this time it's a different kind of system. It is a render system which is used to actually draw something on the screen. Render systems are defined using the render system macro, which takes at least 3 arguments. The first is the name of the system, and the second and third are the name of the vertex and fragment shader. A render system basically iterates over all entities that exist and checks whether it has the required components for the vertex and fragment shader. And if it does, it executes the corresponding draw call. In this example, a draw call is issued for every entity that has vertex position and colors and the transform component. Because the vertex positions and colors are flagged as vertex attributes in the vertex shader, the framework will create the corresponding vertex buffers and fill them correctly. In addition, it will create a uniform buffer for the transform matrices and bind everything correctly before the draw call. It also updates the buffers every time the context is changed. Here, I only change the transform matrix every frame, but it is also possible to dynamically change the vertex attributes using a system, and the framework will take care of the rest. So, after talking about the framework for so long now, you probably want to see it in action. And for that, I have an application open that is very close to the example I just showed you. There are a few minor differences because the framework is not quite there where I want it to be yet. For example, every entity component array that is used as a vertex attribute later must also be defined using this vertex attribute macro. But please ignore that, that will go away in the future. Also, using the spawn parameter of the create triangle system also needs this additional attribute before, but this is also redundant information, as you can see. So this will also go away in the future. But for now, I still need it. Otherwise, it's basically the same. We have a create triangle system. We have the rotate system. We have the vertex and fragment shaders. And then we have the definition of the render system. Please ignore the somewhat convoluted name of the vertex and fragment shader. This will also change. And then there's this additional initialization function down below here, which basically tells the framework which systems and which components there are. But there are also ways to automatically get this information. So this might also go away in the future. So now that we have this, let's execute it and see what we get. And this is basically it. This is what we expected. We have a triangle because we emitted 3 vertices here, 3 vertex position and 3 vertex colors. And it's rotating because we updated every frame. And the cool thing here is now, first of all, I can basically change the vertex colors and vertex positions in code. I don't know, let's do something like this. And what did I do here? Shouldn't it be? I didn't save. Okay, never mind. So when I save, you get a different kind of triangle with different colors. Let's change the position back. Okay. For example, we can make it all red like this. But what we can also do, and this is, I think, very, very cool, we can directly manipulate the vertex and fragment shader in here. For example, we can kick out this transformation for now because we don't want it. And like that, the triangle is not rotating anymore and it's just static. So we just edited the shader, just ran the application again, and everything was fine. We can also say, I don't know, we don't want the color to be a vertex color because it's a solid color anyway. So let's make it entity color like this. Let's make it an entity attribute. It's a vec4. And so it's not an array anymore, but we just give it, we just make it red. Anything else? Yeah, down here, the vertex color there. Oh, we need to change this here. It's not a vertex color anymore, but it's now entity color. And down here, it's not a vertex attribute anymore, but just like this. And when we run it again, hopefully I didn't, this is not, we need to change this here also. It's entity color now. When we run it now, boom. We just changed the vertex attribute from or we just change the color from a vertex attribute to an entity component. So, but it still functions the same. And under the hood, the framework connected all the different buffers that it needed, and everything just worked. And we, can continue to edit the shaders, for example. Let's make everything a little bit darker. I don't know, because it's too bright. Let's do it like this. And now the green got a little darker. So these are the basics of the framework. You can also do like more advanced stuff. I'm currently working on a small particle demo. You can not see much here. Also, what I want to do is like multi-viewport, multi-GPU rendering. So we can split the scene up into multiple viewports, which can be rendered by multiple GPUs and stuff like that. So stay tuned. This is just the beginning. And that's it for this video. I hope I could give you a rough overview about the concepts behind the Ovis framework. In future videos, I want to talk about more specific topics in more detail. The framework is also super early in its development, so it's still missing a lot of features and I have a ton of ideas in my head I still want to implement. Until then, you can try out the framework on a website I created on ovis3d.com. I'm still trying to get the documentation in a useful state, but until then, you can maybe fiddle around with the example a little bit. And if you have any feedback, questions or suggestions, I would love to hear about it in the comments. Thanks for watching and see you soon.